Good morning, student. This is your optical communication sessions, which is digital classes we are considering. In today's sessions of optical communication class, I am actually going to explain you about the group delays, determination of it, how the group delays is being used, and what are the various part that group delays depends on it. And we are going to mostly concern with our discussions as well, how this delays can be used to overcome all the determinations of your information capacity determination part we are going to see, and the basic analysis part, how the losses we already covered losses part, only the further part of losses we are going to consider. The concepts are related to the determination part, group delays and everything. We are more concerned about that, and once we complete that one, we are able to find out the analysis part. So once we applied that analysis part, we can able to see their group delays. Okay, students. So we are concerned with that, and once we are concerned with those kind of category, we can able to analyze the information part. Information in the sense whatever the delays we are considering, how effectively we can find out their analysis and how we can overcome from those analysis part. Even that also we are going to see. So before starting today's sessions, let's take a quick recap of previous sessions, what we discussed. So in the previous sessions, we talk about students, the dispersion losses, all types of losses we covered, and even we see some of their part why the losses occurring, like absorption, scattering, bending. If you talk about dispersion, if you talk about scattering types, if you talk about linearity, non-linearity part, how why we get SBS and SRS, everything we talk about in the previous sessions. In today's sessions also we are more concerned with their data, with their actually the more details of it that we are going to consider, and apart from that we are going to see their analysis part also. So when we are going to complete that analysis, we are going to see their application as well. Take a quick recap, students. In the signal part, what we learn about attenuation, right? We start from the attenuation part, we learn about that, and we have proceed with the attenuation, how the attenuation is going to affect the overall signal, because mere concept of our is what, why we lost or why we get the attenuation. This is our questions. Why and what degree do signal get distorted and they propagate along the fiber. So basically signal attenuation is nothing but is one more name for that is fiber loss or signal loss. One of the name is same. So one of the most important properties of an optical fiber is that because it largely determines the maximum unamplified or repeated less separated between a transmitter and a receiver. When we do have a transmitter as well as when we do have a receiver, we get the mechanism for getting the signal get distorted. The distorted mechanism in a fiber that causes optical signal pulses to be broadened in the sense to get the enlarged. So as they travel along a fiber, the signal distortion mechanism thus limits the information carrying capacity. So because when we get distortion, whatever the signal you are trying to pass to the sender to the receiver, from transmitter to the receiver, it not get completely 100% received. It may get distorted, or it may get broadened, or it may get broadened as they travel from the fiber only, because we are getting the information from the fiber only, right? So what are the things we'll get? Suppose this is a diagram, I'll show you. What is the diagram is all about? It is about non-linear scattering. As you can see here, this is my optical fiber, right? This is my different wavelength, lambda 1, lambda 2, lambda 3, lambda 4. This is my wavelength I am sending. And this end also I am showing you the wavelength so that I can understand the interaction of light wave with phonons in the silica medium. So if you do have a silica medium inside the fiber, when we are transferring these kind of different waves with different length, the energy get transferred from lower to the higher, right? Always we know energy travel from lower wavelength to the higher wavelength, lambda. So whichever lower is or whichever higher is, that will take into that. As you can see here, self and cross phase modulation. When we do have a self and cross phase modulation, so where we'll get this kind of modulation in your communication techniques. When you try to pass the information, when we are traveling the information, see here, what is the information? This is a transmitter, right? This is my complete modulated signal. I just want to show one particular loop. That's the reason I've mentioned like this. So this is my fiber, no? Fiber is my medium. From the fiber only, we are passing our information. So fiber, it is getting received from other end. From other end of the fiber, it is getting received. When we traveling from the transmitter to the receiver, it needs to receive the one which I am giving. But what happened to this? The phase angle depends upon light intensity. Whatever the light intensity I do have depends upon that my self and cross phase modulation is going to occur. This is called as SPM, self phase modulation, and self and cross phase modulation. So phase means it depends upon the phase, right? Phase means angle, phase angle. So that needs to be in phase only. If it is out of phase, then if I send hello, then it will receive reverse hello, hello. Hello if I send OLLEH, it will come in the reverse manner. If it is in reverse manner, then what is the use of it? It should not be giving the proper information what I am sending, right? So that needs to be in a proper phase. Phase angle depends upon light intensity. What is the light intensity? Phi is equals to gamma pin. Pin is nothing but input power, then length of your particular fiber. L effective for SPM. So L effective is nothing but total length of the fiber, effective length of the fiber. So this is your 5 actual phase. If you want to find phi 1, then how many input power? P input 1, input power 1, input power 2, input 3 into L effective for CPM cross PM, or we can write it as CPM. So or XPM. So this is, you can see in the diagram. So as we are seeing here, right, this is information we're passing from self and cross phase modulation. So cross also we can write as X. This X indicates what? Cross phase modulation, or CPM also we can write. Clear? Self phase modulation. Next is, if you are taking 4-wave mixing. As you see, students, what is the wave, what is the frequency we are considering? This is our main frequency now, F1. This is your F2, F3. I'm taking different. All are having different amplitude and different frequencies. So when we are taking 4-wave mixing, FWM, when I'm taking the 4-wave, I'm getting mixing for that. It gives rise to new frequency. It combine all this and it try to produce a new frequency, right? So these signals appear as a crosstalk to existing signals. Suppose one person is talking, like if you see the walkie-talkie of any kind of policeman or something, if one is speaking, the distorted signal will come to the all other receiver. Transmitter is one end, but the receiver is many. So whatever the distortion is there, when you see on the road or somewhere, they get the signal, but they'll get a lot of noise around that, because they will get the crosstalk, right? They get the whatever the crosstalk of others and also get there, that's going to add up the noise to that particular signal. That it is not a desired one, right? Because whatever the information we are sending, we are getting that, but it is not in a proper form. So we need to make it in a proper form. In order to get that, the signal should produce a new frequency. So these signals appears as a crosstalk to existing signals that affects in higher when delta lambda is less. So whenever delta lambda we are considering, delta lambda is nothing but change in the wavelength. So when we see the change in wavelength, we can say that FWM, the frequency, whatever the frequency we are putting for this FWM, it is getting completely. See, we had F13, F12, all those things. These are 4-wave mixing. So this is called actually the 4-wave mixing. So whatever the frequency we are getting for 4-wave mixing, how can we get that one? We can get from CWDM into WDM into DWDM. This is actually the way we can get the crossover talk for that particular signal. Clear? So whenever we try to find out this kind of application for getting the frequency, actually our main concept is what? Whatever the information we are sending from the transmitter, the same information we should receive at the receiver end, but it won't get that particular part to the receiver end. So in order to get that desired signal, we need to remove the undesired signal from that. That is called as attenuation. So what is attenuation part? The loss of signal, or the loss of your variation of the signal. So whatever the loss we are getting, that is called as attenuation. Okay. So as you can see see here. So what I can see for this, just a moment. I just want to show you the proper one so that it will be easy for you to understand that particular information, and you can understand the graph. If you understand the theoretical part, you can maintain from your own way. So just a moment. So whatever the attenuation we are considering here, that needs to be crossover talked. The crossover talk in the sense, see here. So let me enlarge that. See here. If I take a distance, if I take a signal, what is the signal I'm taking? This is my power signal. This is my information, right? I'm sending from optical fiber and I'm getting the noise. See, this is much amplitude. I do have signal, but what else I'm getting in that? I'm getting the noise also, right? So this is what effect of attenuation and noise to our medium. So that needs to be reduce the signal power during transmission, limits to the length, and it is also see how far you are sending the information. So this is the way it gets added up. Next part, whatever